Hi, everybody. My name is Stephen Ruiz. I'm a powertrain calibration engineer by profession. I work with Automotive Consulting Services, or ACS, as calibration manager, and I'm here to talk to you about emissions calibration and testing. Before we start, I would suggest you watch Dr. Pruka's session, Intro to Emissions Formation and Aftertreatment. This will go over the fundamentals and chemistry of emissions formation and help you better understand the material. Intentions of this session. Like Dr. Pruka's session, this session is limited to spark ignition gasoline engines that run a homogeneous mixture. Some of the information can translate over to other engine platforms like diesel, but that will be more the testing and data gathering side of it. We want to provide direction. This talk attempts to provide insight on emissions testing, specifically the sequence, data review, and inherent hurdles. And last, data is important. Emissions testing can be incredibly complex. Collecting and scrutinizing data is what's going to lead the project to success. Here is a test sequence that will be a good guide. Configure thorough data logging channels: engine speed, manifold absolute pressure, load, engine coolant temp, intake air temp, ignition advance, cam phasing, etc. But also focus on channels that will help you model the airflow into the engine: MAF frequency, airflow, volumetric efficiency, barometric pressure, etc. Instrument vehicle: wideband O2 sensors, even if the vehicle has factory wideband O2 sensors. We would want an auxiliary wideband O2 sensor that we could use a auxiliary power supply to capture true cranking and open loop lambda. Pressure transducers, MAP, exhaust back pressure, for example. Thermocouples for post-catalyst temperature data. We'll talk more about this later. Perform baseline emissions testing, FTP 75, USO 6, and SCO 3 on a instrumented vehicle before modification and calibration. Request modal data. This will show you where in the test the emissions are accruing for a specific species. Request PM sample. Most new vehicles will have a PM standard. This is important on DI vehicles because of reduced time for the injection event and atomization. Also fuel impingement on the piston. Capture true cranking and open loop lambda. Compare emissions test results to standard and cert value. Also review modal. Also make sure deterioration factor is applied. This will account for a catalyst aging. What the baseline testing will also do is prove out and make sure we are using a good example for our platform. Configure calibration accurately for mechanical components: injectors, pressure transducers, thermistors, etc. For example, turbochargers and supercharger applications might need high flow injectors. We need to input the flow correctly. This will most likely, on newer vehicles, be constant injector pressure, varying injector delta, also battery offset and latency. Transfer functions for pressure transducers used for MAP. Maybe replacing this so the MAP can read P ratios above 1 for force induction applications. Transfer functions for thermistors like air intake temp, etc. We also need to think about evap emissions and not just tailpipe emissions. This pertains to intake changes that might have hydrocarbon absorbers from the factory or LEV3 evap injectors. This is a discussion in itself, but we want to pay attention to this. Calibrate to retain OEM emission control strategies like catalyst light off, DFCO, catalyst reactivation, emission component durability strategies like COT, catalyst overtemp. Calibrate to retain OEM diagnostics, DTCs, and readiness monitors. You will not be given an executive order if you're not able to complete every applicable readiness monitor. This is a priority, and we need to test for this. We cannot cal out or disable DTCs. It is possible we might need to calibrate the threshold for things like a baro map, airflow correlation, peak load, or airflow DTCs, for example. If this is needed, we will want to keep the same error delta allowed as the OEM strategy. There are some cases when you might want to disable DTCs for intake runner control, for example. This might be in a case where you're mechanically removing it because of an intake manifold change. This would have to be divulged in the calibration modification log, and this is a discussion in itself. Calibrate fuel control to minimize closed loop error. We want good fuel control. This is very important. Having good fuel control will limit closed loop error and tighten up transient maneuvers like tip in and tip outs. Bottom line, closed loop fuel control will have delay before it can rectify an error because it first needs to see the error before it can respond. Long-term fuel trims help with this control, but inherently there will be a delay. Validate calibration in environmental extremes after you have reached a mature state with the calibration. Test at altitude above 7,000 feet, higher the better. We might have ignition and fuel multiplier work to do here. Temperature extremes. Below 0°C, we will need to test fuel control. Above 38°C, we will need to test power derates because of high ECT and IAT, also ignition modifiers. Tow tests if the platform can be used for tow testing. This is a thing we should do. After the calibration and components have been tested and we are happy with results, perform engineering emissions testing, FTP 75, USO6, and SCO3 on an instrumented modified vehicle, like we did on our baseline. We want to request modal, PM sample, capture true cranking and open loop lambda, compare emissions test results to standard, and review modal. Again, make sure the deterioration factor is applied. And now, make calibration changes to bring down pollutants if needed. We will talk about this more obviously. Depending on the calibration changes needed for emissions, we might need to validate the calibration or components to meet our targets, drivability and power, for example. We need to sell what we certify. Here we graphed our modal data per species or pollutants for the FTP 75 using concentration. We have graphed hydrocarbons, NOx, and CO using their own separate graphs. We have also graphed them in a way so we can change the resolution. This is important so we can focus on different parts of the test in detail. Here we have focused on the cold start portion of the FTP. We have chosen to focus on the first 35 seconds. Like mentioned before, with the modal, we can see where the emissions are accruing. We can correlate the modal data to our data logs, so we can zero in on the operation that could possibly be causing our emissions. Also, notice the delay in the start of the modal and test. 0 seconds is the start of the test, but the modal doesn't start producing data until about 8 to 13 seconds after, depending on the species. This will have to be accounted for during the length of the test. Now we're going to focus on the engine start. During a cold engine start, tailpipe emissions will equal the engine out emissions, because the after treatment or catalyst is not active. Because of this, a majority of emissions will accrue during the first phase of the FTP. During phase 1 of the FTP, the ECT, IAT, oil temp, catalyst temp will be around 20 to 30 C. This is the test lab requirement for ambient temperature. This is also after a specified soak to normalize temperature. The catalyst will become active at around 250 C. we want to focus on getting the catalyst to this target as fast as possible. To aid in this, we should target about 10 to 15 degrees after top dead center for the ignition advance. This is what is referred to as catalyst light off. This strategy will send the energy or heat out of the exhaust to the catalyst. Catalyst light off will last about 10 to 15 seconds in total, sometimes longer depending on the strategy. This will aid in the catalyst reaching 250 C in about 110 to 130 seconds, sooner the better. If we have an application where we have affected the relationship of desired and actual load, we might need to rectify errors before catalyst light off works as intended. Like we mentioned before, during a cold start, our tailpipe emissions will equal the engine out emissions because the catalyst temp has not reached the 250 C target to start reducing our emissions. Because of this, we need to have good fuel control. Also, we will have closed loop fuel control. We will not have good closed loop fuel control to help us for at least 7 to 10 seconds after the engine start. To check our open loop, closed loop fuel control, we need to have a wideband sensor powered up to auxiliary power source. You could use the battery power, but usually not ignition power, because during a voltage drop, because of start, the wideband controller will restart and you will miss the cold start lambda data. Here you can see the peak rich lambda value is about 0.82 to 0.83 lambda, and then steadily leans out to our target. Ideally, we want to reach stoic in about 10 seconds after our peak rich event. We also don't want to go richer than about 0.77 lambda during the peak rich event. We also want to be careful not to misfire during this time, as this will be bad, sending raw hydrocarbons out the tailpipe. This can happen when you try to go too lean during a cold start and affect the combustion efficiency while doing so. A side note, you can see we started the test at around the 30-second mark. This is on the data recording or data log. This helps us line up the modal data or modal delay easier. Like mentioned before, we will not have the help of closed loop fuel control for about 7 to 10 seconds after the engine start. You can see where the closed loop fuel control engages around 10 seconds into the test. During this time, it looks like we had a 3 to 5% error. We want to keep this error as small as possible. Here we have a lambda target comparison. This is so we can generally understand what different lambda values can do to our test. Let's first observe the dithering. The dithering refers to the lean and rich swings, regardless of the target. The blue line, for example, this is the target lambda at stoichiometric. For road fuels and emission cert fuels with 10% ethanol, this is an air-fuel ratio of 14.08 to 1. You can see the dithering is between 1.01 to 0.99 lambda, a delta of 0.02 lambda. This will help the conversion of all species using our three-way catalysts: lean to oxidize hydrocarbon and CO, and rich to reduce NOx. The peak-to-peak transitions will last about 800 milliseconds at lighter loads and lower engine speeds, like we have represented here, and 300 to 400 milliseconds at higher engine speeds and higher loads. Depending on the results of a test, a leaner target around 1.015 lambda will help reduce hydrocarbons and COs if needed. A richer target around 0.985 lambda will help reduce NOx. The thing we need to keep in mind is the emissions might start to seesaw very quickly depending on how this is done. If you don't have access to the control target and try to use this method, the field trims will eventually erase the work. Here we have a dithering comparison. All graphs have the same target. If you pay attention to the middle graph, we have neutral dithering. It spends the same amount of time lean and rich. The top graph spends more time lean, and the bottom graph spends more time rich. For example, if you need to reduce hydrocarbons and/or CO, you can try and change the dithering to spend more time lean compared to rich. Refer to the top graph. As an example, at lower engine speeds and loads, you can spend 400 milliseconds lean and 200 milliseconds rich. There will be time used for the actual transition. Some refer to this control as controlling the O2 bias. If you wanted to reduce NOx, you can spend 400 milliseconds rich and 200 milliseconds lean, like represented in the bottom graph. Here we have an example of normal transient driving operation, what you would expect to see on phase 1 and 3 of the FTP or during a USO 6. The fuel target is stoic, a lambda of 1. We have fluctuations of the accelerator pedal to modulate torque, the torque that we need to keep the desired speed. Because of this, the manifold absolute pressure, load, and throttle blade are moving as well. We have bank 1 and bank 2 lambda data, and we can see the dithering from around 1.01 to 0.99 lambda on the right side of the graph. We can see the transient fuel control tip in and tip outs during the accelerator pedal movement and map transitions. They are controlled and consistent for the most part during these regions. We can also see that during the transient movements to 0% pedal, we have DFCO events. DFCO is decel fuel cutoff. DFCO is a common strategy to improve fuel economy when no engine torque is required. We have 4 events here. During DFCO, the catalyst gets an abundance amount of oxygen and stores it as well. The catalyst needs some way to purge the oxygen so it can then reduce NOx. The way the catalyst gets purged is catalyst reactivation. That refers to the rich operation out of the DFCO event. These rich areas right here. Catalyst reactivation targets are around 0.8 to 0.887-ish lambda. These events will last for about 2 seconds, sometimes a little longer, depending on the strategy. We want to make sure we don't go too rich. We don't want to go richer than about 0.8 lambda during these scenarios. This is just an overall good example of good fuel control. Here we have phase 1, 2, and 3 of the FTP 75. We have modal HC concentration graph. Also, you will most likely have an NMOX standard that you will need to meet. Some short information about the relationship of hydrocarbons. NMHC, non-methane hydrocarbons, are hydrocarbons without methane. NMOG, non-methane organic gas, is NMHC adjusted to add oxygenated compounds. For example, this is sometimes a 10% multiplier on top of the NMHC value. So using the HC modal is correct. You can see the HC is going to have its highest spike during the cold start phase. Tailpipe emissions will equal our engine out emissions because the catalyst is not activated yet. You can also see the 9 to 11 minute soak period, the area where we do not have data. This is referred to as the 10-minute soak. Phase 3 will be a hot start. You will usually get a little spike during the hot start as well because closed loop control is not available instantly during a hot start either. Closed loop should enable very quickly though during a hot start, maybe 5 to 8 seconds after the start event. During the second set of accels or hills, you will see we have some hydrocarbon spikes. This region right here. This is an inherent hurdle during phase 1. We need to produce a fair bit of torque in this scenario. The engine is cold, and the driver will be inducing transients to stay on the target speed. If we have high spikes in this area where we feel the results are impacting our hydrocarbon emissions, we should first look at transient fuel control. We need to make sure that we are not too rich during tip ins and tip outs. If transients are good, we should try to control our dithering, spend more time lean, for example. Also, remember, hydrocarbons can escape the combustion process with oil getting past piston rings, leaking injectors, bad atomization, misfires because of numerous reasons, etc. If these things are happening, we need to be thinking about resolving them. Here we have modal NOx concentration graph. Again, the FTP 75. NOx is formed at high combustion temps and cylinder pressures. Accel events during emission traces, we will need to be mindful of NOx. Retard ignition advance to bring the cylinder pressure down is one way this can be done. Also, if we have excessive boost during transition and transient events, this could cause NOx formation depending on combustion temps and cylinder pressures. For turbocharged vehicles, if we need to calibrate our boost control, pig control in particular, or depending on the strategy, our torque control, we might need to do this work. If we have lean transitions during tip in and tip outs, we will want to resolve this, as this will create NOx as well. During phase 3, you can see we have an increase in NOx on the second set of hills, this region right here. This is most likely because we have leaner tip in and tip outs, because the engine coolant temp is higher and the fuel control modifiers are slightly different than when compared to colder ECTs. When we talk about transient fuel control, we can modify this by calibrating our transient fuel gain and time constants during tip in and tip out events, accel and decel. The gain will be the fuel mass, for example, and the time constant is the transient rate and time, the transition rate and time. These tables might use RPM and MAP as the axes, but could also have modifier tables that use manifold absolute pressure and engine coolant temp as well. Remember, we can play with the dithering here as well, spending more time rich if we have enough room in the hydrocarbons and CO to play with. Cam phasing is also something we should consider while working with NOx. The relationship of intake valve opening and exhaust valve closing overlap could induce EGR. EGR will reduce NOx. Having too much EGR will create unstable combustion though, so we want to be careful. Phasing exhaust valve closing after TDC will cause residual exhaust gases to remain in the cylinder at the start of the intake stroke. Last, we have modal CO concentration graph, FTP 75 again. CO is formed when we operate at a rich lambda. During a rich lambda, there is not enough oxygen to oxidize CO. CO can increase dramatically when power enrichment is enabled during a test, also when COT or catalyst overtemp is enabled. Power enrichment should only be used for wide open throttle operation. This means it should not be enabled during an FTP, USO6, or SCO3. Even when power enrichment is enabled, during a wide open throttle operation or event, it still has a delayed control. This delayed control should be put in and utilized per gear or after a certain map threshold has been reached, for example. Sometimes power enrichment calibration can be skewed because of poor torque mapping or because we're relying on power enrichment to reduce spark knock, detonation, because of high boost or advanced ignition values. Be mindful of this. Also, when COT thresholds are not calibrated correctly or airflow and load are not modeled correctly, we can have catalyst overtemp enabled too early, and this could cause high CO emissions. Here we have an example of misfire. When logging, you will be able to see misfire with oxygen sensors, wideband and narrowband oxygen sensors. Oxygen sensors read oxygen, or the percentage of oxygen. They do not read fuel. During a misfire, some amount of fuel will not be burned during the combustion process, and you will have raw fuel coming through the exhaust. This will leave us with an excessive amount of oxygen. You will see the lean spikes in the lambda data and the fuel trim data. This will show a definite issue and will cause high hydrocarbons and CO. Spiking lambda data, spikes in the fuel trim data. Be careful of this during the nonlinear range of the injector. A nonlinear range can be thought of as the range you will see the most injector to injector deviation. This will happen at lower pulse widths, for example, under 1 millisecond. We need to also be careful of misfire for another reason. Misfire will send catalyst temperatures very high because of the reaction unburned fuel and oxygen will recreate on the face of the catalyst. We have talked a lot about catalyst temps a fair bit. Catalyst temp targets for activating the catalyst after a cold start, catalyst overtemp to control catalyst temperatures. When we talk about catalyst temperatures, we are talking about mid-bed catalyst temps. The catalyst mid-bed starts about an inch back from the face of the catalyst substrate. Post-catalyst temp data is less intrusive to instrument because we don't need to have an instrumented catalyst by setting a thermocouple into the substrate. We set a thermocouple about 1 to 6 inches back from the end of the catalyst. This is a fair bit easier. With this method, we do need to account for some temperature drop though. 6 inches back from the end of the catalyst will result in a 30 to 40 C drop in temp. This needs to be added to the post-cat temp data. Here we have a USO6 trace with a modeled catalyst temp example. Catalyst temp read from the ECU is almost always modeled and is not actual. This is done by the OEM for the stock vehicle. If we change airflow, load, or torque, we will most likely affect this model. We need to be mindful of this and calibrate to correct the model for our specific application. At least verify the model. You can see higher loads or torque because of acceleration cause higher modeled catalyst temps. Here, here, and here, you get some fluctuation or increase in this region as well. If the model temp is higher than actual, COT will be too active. This will cause high CO and high hydrocarbons, for example. Lower than actual, catalyst damage will occur. If damage occurs, this will also affect the emissions. We need to take care of emissions components or after treatment durability. This will also cause reliability issues and warranty claims. Ideally, the correct threshold and enrichment targets during COT are values that are that normalize catalyst midbed temps to no more than 900 C. If you want to go higher than 900 C, you should have testing to support this. It is not suggested. Summary. Configure data logging equipment to give insightful data on engine operation, fuel control, ignition advance, cam phasing, temperatures, pressures, etc. Most importantly, parameters that will help us model airflow and volumetric efficiency. Baseline test vehicle. Is it a good exemplary vehicle? Configure calibration accurately for specific components. Also, pay attention to EVAP, the EVAP emission standards. Good fuel control is crucial. That's a bottom line. Calibrate to retain OEM emissions control strategies, emission component after treatment durability strategies, and diagnostics. Validate calibration and/or components. For example, weather extremes, tow testing, elevation testing. Emissions test the calibration and/or components. One of the most important parts of this whole thing. Validate calibration and/or components that were modified during the emissions testing process. And the most important part, sell the product that has been represented and certified. We need to have high integrity here. Thank you, everyone. This is a lot of information on a very complex subject. We could talk about this for a very long time and get into greater detail. I hope this information helps. If you have any questions, my email is below, and have a good day.